Okay, this is section 3.4 from your Math Links 9 textbook on applying exponents in context. So the two show you knows ask you to use a formula to solve the problem. So the first one says a right triangle has two shorter sides that measure 8 centimeters and 15 centimeters. So it's right here. Here's your right triangle right here. It says, what is the area of the square attached to the hypotenuse? So in order to solve this, we kind of have to have some sensible memory of what Pythagoras had said. And he said that the side lengths of the two legs, if we attach squares to them, and we add those, we calculate the area of those two squares, the area of those two squares added together, or the sum of the area of the squares attached to the legs, will equal the area of the square attached to the hypotenuse. So if we think about that, that means this area is 64, and this area is 225. Now what we could have also done is simply use the formula, which was a squared plus b squared equals c squared. And then I could simply plug in my legs as 8 squared plus 15 squared will equal the area of the square attached to the hypotenuse, or c squared. So 64 plus 225 equals 289. And 289 equals this square here, or the area of the square attached to the hypotenuse. So your answer for that is, therefore, the area is 289. In your second part, it says, what is the surface area of a cube with an edge length of 3 meters? Now, just to kind of quickly remind you that a cube, back in grade 8, you broke it down into a net, and you realize that a cube has 6 faces, and each of those faces uses the formula side squared to calculate the area. So if we think about how many faces there are, if one face is side squared, then multiplying side squared by 6 will allow us to calculate the entire area of all of the faces combined, which is called your surface area. So if I substitute the side length, or the edge length, of 3 and square that, I would get 6 multiplied by, because I'm going to follow BEDMAS, 9, which is 54 square centimeters for the entire surface area of that cube. Okay. So all we're really doing is we're applying exponents of 2 into our formulas that we learned in grade 8. Our second section, hang on one second. Our second show you know says a type of bacterium is known to triple every hour. There are 50 bacterium to start with. How many would be after each number of hours? So we're going to make a table here to start. And we're going to call this one H for number of hours. And we're going to call this one B for number of bacterium. All right, so number of hours in bacterium. So after 0 hours, since it started with 50 bacterium, after no time, there are going to be 50 bacterium in whatever dish is holding these particular bacterium. After 1 hour, those 50 bacterium are going to triple. So we're going to triple 50 to make it 150. Okay. So now after 1 hour, there are 150 bacterium in the dish. And then it's going to go for another hour. So we're going to have hour number 2. And that 150 bacterium is going to triple, making it 450. After 3 hours, 450 will triple. It'll become 1350. After 4 hours, we will triple the 1350, giving us what is that, 1350? I better do that in the calculator. 1350, and we'll triple it, which I have a button right here. That's not tripling it. Times it by 3. It is 40,050. The brain wasn't working. And finally, if we go for 5 hours, that 4,050 is going to triple, giving us 12,150 bacterium. Okay? So how many will there be after 5 hours? The answer is 12,150. After 3 hours, there'll be 1,350. But then this last one says after T hours. Okay? So what we need to do for T hours is it's asking us, can we devise a formula that will work to calculate it? And the answer is yes, there is a formula for exponential growth. And what that is this. So we're going to have our starting number multiplied by the rate of change. And then what we mean by that is like doubling is 2, tripling would be 3, quadrupling would be 4, etc. So multiplied by our rate of change, and then our exponent is number of time units. Okay, number of time units as an exponent. And that's actually the formula for exponential growth. So what does that mean? So we take this question here. Our starting number of bacterium was 50. So I'm going to put that where my 50 was. Actually, let's start first by making it a variable only formula. We're going to say the starting number is going to be represented by S multiplied by the rate of change, which we'll call R. And in the top corner, we're going to call it T for the number of time units. So starting number is S, rate of change is R, number of time units is T. Okay, I'm going to erase this now. So what is our starting number of bacterium? It was 50. So I'm going to put 50 here. And our rate of change, it said that it triples every hour. So rate of change is going to be tripling, which we're going to use as the number 3. And the number of time units, if I take any of these, just to double check it, if I take, let's say, the 5 here, and I'd say after 5 time units, or after 5 hours, how many bacterium would be in there? Well, now we have an expression that we can simplify. We're going to do our exponents first. So 50 multiplied by 3 to the exponent of 5. Grab my calculator. 3 to the exponent of 5 is 243. And if I take that 243 and multiply it by 50, I get 12,150, which is how many I got when I took 5 as my number of time units, or 5 hours. So the formula does work, and we're going to call it starting number multiplied by the rate of change to the exponent of the number of time units. Okay? And it's as easy as that.